Hi, I'm Martin. I work as a software engineer in Zurich in a company called Archaeologic, and I really, really love the web. I have been a web developer for 11 years now. I would call myself a full stack developer because I also work in Scala and Java and stuff, so it's pretty cool. But I really, really love the web, the openness and the low barrier of sort of using it, right? And okay. Nah, not really. Bye. Um, the internet, you know. As I love the internet, I have it all the time. Except now because I just sort of threw it away. Right. Anyway, so yes, I really love the web, and you might now go like, web and 3D, how does that go together? It goes together really well, as it actually turns out. So this is what we are doing. This is a house that has never been built, but you can still walk through it, and you can change the furniture, and you can sort of play around with it, and actually remove things and juggle things around a bit, all from the comfort of your browser. And this is what we do. And so what I'd like to tell you today, coming from sort of that, what I'm doing right now, I want to open up what you can do with 3D on the web. Because lots of people go like, yeah, I heard WebGL is really cool, and you can do really cool stuff, and I've seen this toy and that demo, but it's not really relevant for what I'm doing, and actually that might not necessarily be true, and I want to show you what use cases there are and what you can do with it. Also, what exactly are WebGL things and the APIs, and what is a shader doing, and what's sort of like the basics. So who here has already worked with WebGL? Okay, so I gotta do some very quick introduction things, but I was told to not do beginner things, so if you're interested, you get access to the Topconf University, so you can check out my talk in Tallinn last year, where I gave a very basic introduction and was told that was too basic. But I'm not gonna sort of throw over all sorts of weird stuff and you're gonna go like, what the hell is going on? And you're not gonna see too much math. We're also going to see how you actually optimize 3D performance, because one of the things that the web sort of throws at you as a developer is the fact that you encounter devices with very, very different capabilities and very, very different performance and actually different specifications on what they can and cannot do. So you sort of have to deal with it, right? That's what the web is about, really. And then we're going to go one step further, because, you know, showing things in 3D is one thing, but putting the user literally in the center of what's happening is really, really cool stuff, and that's what virtual reality is about. And I brought some stuff with me to play around with it, and it also works from your browser, including your mobile phone's browser. And I'm just going to wrap up because I only have 40 minutes. I could actually talk about this for days on end, but definitely feel free to pop by and ask questions or drop me lines. So first thing, what is 3D on the web doing? Does it actually make any sense? And the problem with 3D is you can very easily absolutely jump the shark. Who knows this scene? Okay, it's from Jurassic Park, and this wonderful young girl here is trying to open a file, right? And she has to do real quick because she has to do something in this file to close a door, and there's a velociraptor trying to eat people. And she's like, yeah, I got this. I know Unix, because you know everyone that works with Linux or Unix or Mac OS does that. And actually this program exists, I figured out. It's like, what? So every time you want to sort of open a file, you have to navigate through 3D space and then go into the room that is the directory and then open the file. It's like, that makes absolutely zero sense, okay? This is bonkers and it's absolutely jumping the shark. But this one, on the other hand, is kind of cool. So here's an article that talks about a particularly tricky climb of a particular mountain. That's New York Times 2 years ago. And it's really cool because you can actually, so it's nice because it progressively enhances, right? So you have the actual article content here, and that works entirely without the entire, so if you just had no 3D here, you still have pictures and article. So you can read it no matter what. Even if you have JavaScript disabled and CSS disabled, you still get black text on white space, so nice, and some images. But if you actually do have WebGL available, it's really cool because it actually gives you a better understanding of why the frick this has been so hard and is worthy a story. Because I'm from Switzerland, I'm like, yeah, some people climbed the mountain. That's what I do all day when I walk to the office. And so what's the deal here? And then you see this and they're like, yeah, no, I will take the elevator. So yeah, it's pretty cool here. Oh no. Oh no. Progressive enhancement, this one didn't work. The worst case is I have PDF slides because I progressively enhance. The good thing is, that's bonkers, no? Let me quickly see, oh shit, it's now down there. Hurrah. Please. No! Oh, it's probably because it's trying to, let's try this. Oh, bugger. The Linux experience, you kind of get used to it. In which case, let me, that should be cleaned up at some point. What, where? You can actually, yeah, I should totally do 3D things. Is it here somewhere? Please tell me it's somewhere here. Probably going in with G. Shucks. I was pretty sure I had it. Don't have it like here. Yeah. Yeah, that would be cool. That would work. Because I can't find it on the screen right now. That's... Holy shit, that's a long password. Yeah, it's fine. Lucas iPhone, yeah? Jesus. Lucas, where is it? Things are gonna get great. I'm pretty sure I downloaded it yesterday because I'm like, yeah, I'm not gonna risk internet problems, and here we are. So it's possibly in downloads. I just go for it. If you find it, you get something from me. I don't know what yet, but Jesus freaking Christ. Should be something like going in. We are going in. What stupid dick I've been yesterday night. All right, how do I actually get it into a proper F5, you say? Let's see. You're right. Thank you very much. You saved the day.
I was searching for this yesterday.
Okay. So no GIFs, sorry. Another interesting application is this. So on the left-hand side is the Matterhorn, and it's actually, they had drones fly around and scan it in 3D, and had fuck tons, and that's the technical term, not a swear word, of data points representing the Matterhorn, and you can actually zoom in and actually rotate it and get an idea of how it actually looks and works, and where you could possibly get up or not. Like me, I'm not gonna go up, I just eat chocolate, that's all what I take from Switzerland. Or this is a 3D visualization of ski routes. So you can actually have navigation over ski routes in 3D, which is really helpful because actually figuring out if that tree is the tree that your sort of mentor meant when he said like, and there you have to turn left, is a bit trickier than actually figuring it out here. Other visualizations that are beautiful GIFs, sorry, is this, which is you can actually sort of use your phone and then actually turn around and you see the Cathedral of Palma de Mallorca, which is nice because if you haven't been there or can't go there, it's just nice to see great architecture. And this young gentleman is actually walking around using the Oculus Rift, walking around in an in a residential building that doesn't exist yet. If you're an architect, that is invaluable because you're like, I don't know if the lighting conditions work in this building, and you would have to sort of, well, build it, spend a couple millions, and then go, no, they don't. That's hard to fix. Here, it's easy to fix. You literally can just drag the wall and go like, yeah, that's much better. So that's pretty cool. So quickly wrapping that one up, spatial data, everything that is about space. We perceive and live in space all the time. We perceive it in 3D. If you represent it as 3D, that is much, much more natural and much easier to sort of approach for people. Also simulations, so you can simulate like how the light looks in a building, for instance, when the date time changes and the day of month changes and the month change, or do fluid simulations, all sorts of that stuff. Navigation, because a lot of people actually have problems reading maps. But you're kind of good when the thing you see in the real world sort of resembles what you see on your phone. You're like, okay, no, not this street, but the next one, because this building doesn't look like this building, so I'm just going to go forward. Storytelling, also really interesting, as films and comics and pictures have been used to tell stories. You can actually tell stories in space if they are about space. If you try to convey how large something is, how far-reaching a space is, or how very tiny and sort of claustrophobic it is, you can actually transport that. Scientific visualizations, medical data, for instance, can be nicely visualized. So just imagine doctors having to coordinate a operation with an expert on another continent, right? That has been really hard, and they had to sort of install applications and stuff. Now they can do it from the browser, which is the original idea of the web. The original idea of the web was to sort of share knowledge very easily without having to sort of install things or download things and shift them around. So that's really cool. And obviously games, right? You can do games as well in the browser using that. So with that, we actually go into the technical part. Quick overview. So who here has worked with Canvas? Who here? Yeah, okay, I don't really know who has worked with WebGL. So the Canvas, I already got the question a couple of times. The Canvas is already GPU accelerated. So what's the big deal about WebGL CPU acceleration? And I'm like, well, you know, I don't like to do this, but I'm like, well, actually, actually, people every now and then. Actually, it is not really GPU accelerated. Only the actual getting the pixels onto the screen is GPU accelerated, but getting what pixels you actually want to draw on is not GPU accelerated. So that means you have to have JavaScript, so the CPU actually put things into a buffer and say like this pixel green, this pixel red, this pixel blue, and then actually the GPU takes over on there. So you have to sort of waste your CPU time actually getting the pixels ready for painting. On the other hand, the GPU acceleration for WebGL is also, you can literally say like, I have this data, transform it like that, now transform it like that, move it over there, make it larger, rotate it, so the GPU actually does the heavy lifting for you. So you only say like, do this one thing, and then it does the thing for you. So you don't actually have to waste your CPU on that. You can do clicking and stuff. So that's pretty cool. Another thing is the GPU is so much more powerful doing that because it's specialized for it. The CPU has a problem doing graphics because the CPU has to deal with all sorts of your horrible programs that you write, which is, so the CPU usually doesn't know what's going to happen next, really. They do some sort of prediction and caching, but actually the problem is you might have a loop that modifies the thing over and over again. So it might be like, this step that I'm doing here produces something that is the input to the next step, so I can't do this like all in parallel. I can't do these two things in parallel because, you know, this thing won't run without this thing happening. So I have to sort of wait for it. And the GPU doesn't do that. The GPU gets data, like, okay, these points, these colors, and then pushes them onto the screen. And that is very highly parallelizable because you don't have any of these dependencies. Nice. Also, you have to deal with task switching on a CPU because you know you might actually switch to another program. But the GPU basically doesn't care because it just gets random programs, give it random information to sort of put onto the screen. And it goes like, yeah, whatever. Oh, that's a different program. Pfft, that's not my problem. Like, oh, you said I draw this, I draw this. And makes it really, really fast. Few vocabularies for people who haven't been working with WebGL or 3D much. So first of all, computer graphics people love to invent new words. So like, let's invent new words. So how do we name the points that we put on screen? And my intuition says points. But they're like, nah, you know what? We're going to say vertex. And because it ends on an X and English is fun, it's going to be vertices. So irregular plural, double trouble. So yeah, a vertex is nothing else than a point in 3D space. Next. And now you sort of have the points, but you sort of want to know what shape they actually form. So you define faces. Faces literally are just a list that says point 1, point 2, point 3, one triangle. Or rectangular, or whatever. But actually you use triangles, because with triangles you can actually sort of approximate every shape that there is. If you take enough triangles, you get a circle, if you do it right. So, okay. And then there's a thing called normal, or normal vector. And that's literally just saying what side, what direction is a thing, as a face sort of looking at. So this, for instance, the normal vector would go like this, because it's facing that way. My normal vector is like this, at least for my face is like this. Right? My finger now goes like this, and so on and so forth. That's normal vectors. You see them here and here. So that's normal vectors. And this would be one face, probably two, not necessarily one face, but here's one face, one normal vector. And this is useful because you can actually use it to figure out how light works. Just imagine a piece of paper. If the piece of paper is like this, and the light is the beamer, there's a 90 degrees angle between where the beamer, actually a 180 degrees angle between where the beamer faces and the paper faces. So it hits on full intensity. If I would turn the screen around 90 degrees, now there would be a 90 degrees angle, and you would not have any influence on the light, right? So this is very, very useful. And then there's a thing called fragment that we're gonna see and use later on. It's more or less a pixel. If you have heard the term pixel shader, it's slightly incorrect, because nowadays, to make things look very crisp and very nice, we're actually pretending in memory to have more pixels than we're actually having, so that our calculations look nicer and smoother. So a pixel might actually really be like 4 pixels in memory, and a fragment sort of accounts for that and says like, actually this is 4 pixels, but you were gonna make it 1 pixel. That's called subpixel precision. So here you have a fragment that's all the pixels that are non-white on this triangle. So each pixel on this is a fragment pixel, and this entire thing is a fragment. Now, this is the crucial point. You see 3 colors. You see blue, you see green, and you see red. Ignoring red for a second, blue is the only bits and pieces that are happening in JavaScript. Everything in green happens on the GPU. Now, if you would compare this to canvas, on the canvas, pretty much most of this is being skipped, but pretty much everything would be blue, except for this bit. So this bit would then not be blue. But here we actually leverage the entire power of the GPU. And what happens? So we have 2 arrays. One is with the points that we want to put in space. Remember, vertices, because why not? And an array of faces that defines how these points in space actually are connected with each other. We put them into a structure that's called a GL buffer. A GL buffer is nothing else than a piece of memory, a chunk of memory on the graphics card. If you don't have graphics memory separated, that doesn't matter, but it's still a piece of memory that is then used for all the drawing operations later on. And this information, these vertices, go into what's called the vertex shader, and that's basically a program that can be used to sort of manipulate them. For instance, when you load a 3D model, you want to only think about, like, if I have a triangle, I just want to think about these 3 points. I might go have my own coordinate system and say, okay, this is 0, 0, 0, and then this is on the y-axis 1, and this is on the x-axis -1, and this is on the x-axis 1, and then I have this triangle. But actually, it might be somewhere completely different if you actually load it into a 3D space, right? So this might have these points like -1, -1, -1, 1, -1, and so on and so far, but it actually might be over here, completely different coordinates when I look at the entire room, or then here, but the local coordinates are the same. And you can do these kind of transformations in the vertex shader. So basically, the vertex shader is a program that's given every single point, and it transforms it to another point for displaying. That outputs rasterized fragments, so basically it says like these coordinates have to be colored in. And that goes into another program that takes these coordinates and some other data as well that you can specify, and figures out how to actually draw them. So for instance, you can say, oh, I want this triangle to be drawn with a texture of a brick wall. And then this fragment shader will go, okay, so I'm at 0, 0, so I'm going to take this pixel from the texture, and then this pixel, and then this pixel, and actually draws it out. It also does the lighting calculations, so it also gets the angle, the normal vector of your light versus the normal vector of the fragment it's looking at, and you can actually do the lighting calculation here. And that gives you pixels on screen. Hurrah! Now what is this weird red box? The cool thing about these programs here and here is they're not hardware built in, they're not hard-coded. You can write them, you don't have to, but you can write them. Unfortunately not in JavaScript, because you know, you don't really want to do that. You want to have all the convenience functions. So this one is actually written in a different language called, my screen turned off, GLSL, GL Shader Language, Graphics Library Shader Language, or GL Slang, how the cool kids name it. And you can specify it, you can compile it, you can put it onto the GPU and mine bitcoins. I mean, draw things on screen. In fact, you can't mine bitcoins because it's restricted and stuff. So quickly recap. A shader is nothing else than a program that operates on the GPU. A vertex shader gets each vertex, like it's a function that takes a vertex and does something with it and transforms it. You can do things like coordinate system conversion, scaling, rotation, skewing, all that kind of stuff, perspective transformations, blah. And the fragment shader basically operates on a fragment pixel, which might not be a real pixel, but can be a real pixel. And it's used for texturing, lighting, and some fancy effects. So basically, a shader is nothing else than a function in fat arrow syntax to get lexical scoping. Anyway, so you basically have a bunch of inputs, and it gets an output. And here's why it's so easy to parallelize that. There's no such thing as a side effect or any sort of problems with that. You have inputs that are known at the runtime, and you get an output. End of story. It's never going to happen that the output of a shader is the input of another shader, except for the fragments that are the output of the fragment shader, the vertex shader going into the fragment shader. But that's the only sort of thing. That's why you can't really parallelize those. And here's how a shader looks. Don't fear. It's not too bad. So we have attributes, we have uniforms. What the hell? So attributes are things that can actually change on vertex. And uniforms are sort of static. They're not going to change for this entire thing that we're going to draw. So here we have some matrices, like this is the model view matrix, ignore that. And this is the perspective matrix. So this matrix makes it so that things that are farther away are sort of smaller and closer together, and things that are closer to the camera are larger and wider. And you do some matrix calculations here, and you're done, and that's it. Very boring. I actually don't really do much with vertex shaders, you might notice. Fragment shaders, on the other hand, are interesting. So here we get an output that is the color that's going to be drawn onto the thing. As a like 1.0, 1.0, 1.0 would be white, for instance. And then actually there's a fourth one for alpha. So if there's 0, it means it's entirely transparent. If it's 1, then it's actually opaque. And here we go, like we want a coordinate on the texture. And we have, this should actually be a uniform. We have the resolution of the screen. So we sort of make sure that we scale down the resolution of the screen to the size of the texture, and the other way around. And then we define our fragment color as a vector of, for instance, here I just take the x-coordinate, the y-coordinate, and some random coordinates as color. So this is r. So basically what means that it starts with 0, and the further right we go, the further red it will be. And this is green, so the further down we go, the further green it will be. So now we have basically black here, white down here, except for the blue coordinate, the blue component, I'm sort of doing some magical things, and then you get a pretty picture. You could as well use texture coordinates here, but I'm not using that. With that out of the way, let's quickly go over optimizing 3D performance. Definitely recommend you look up the talk about the basics from Talin, really, if you're like what the hell has happened now. So for 3D performance, so this is a model that we did. And it's not one of the largest, and the fun thing is it's only one floor, and this building actually has like 10 of them. But even one floor is quite large if you look at the numbers. So here we're having 1.8 million vertices, so 1.8 million points define this thing, which means that should be actually faces, sorry. 629,000 faces to be drawn, with 557 materials, so that's basically textures and how they reflect light and how they're sort of looking when the light is not there, and yada yada. 149 images that are actually textures. So all this, like how the floor looks and how this looks and how this looks and the green of the plants and stuff, it's all images. 129 million pixels to be drawn, 100 megabytes in your memory. Holy moly, that's 50 megabytes. Just get that. 50 megabyte of download, give you 100 megabytes in RAM. Hurrah! And obviously here you see like there's light coming in from the side, so you have to sort of figure out how to do light calculations, because the only way to really do it dynamically is to actually fire virtual light rays and see how they sort of influence the colors. Pretty tricky to do, and it would horribly be super slow, like 1 frame per second slideshow. Hilarious. So what do? Well, first of all, we don't want to have people wait until 50 megabytes have downloaded. That would be horrible. Not going to bash any other technologies, but there's Unity, which is a brilliant tool for game development. But a lot of people recently discovered, hey, wait a minute, it has WebGL export. So you can actually put your game onto the web with Unity. Awesome. But the problem with that is it's not very webby. Because what's going to happen is you're going to see the Unity logo, and then you're going to see a loading bar. And you're like, what the flying shit? And like after like 30 seconds, you get something. And you're like, no, just imagine that if Amazon would load 30 seconds to show you an image of an article, you wouldn't be shopping there probably, which is there's studies that prove that. So what we do is we start with some basic HTML, and actually we now give you a pre-rendered image, which isn't in this slide yet, because it's not deployed yet. So we give you a pre-rendered image in like 14 kilobytes plus like, I don't know, 50 to 100 kilobytes for the image. And then we load the basic scaffold, because this is very, very simple. This is just a bunch of points and faces, and it's not very large, but it actually makes a big difference because you already see that something's happening after a few seconds. And so we are loading our JavaScript, and then we load the faces and vertices to give you a basic scaffold. And then we continue up with 1 more megabyte and give you basic images for the architectural features. So now you see floors, now you see how the light looks on the floors, and you see wall textures and all that kind of stuff. And then we load furniture, geometry, and very, very low sampled, very, very small texture images for the furniture. So we're now like 4.5 megabyte, still pretty okay. We cache a lot as well, but if you get there with a cold cache, you still it's still more or less fit onto a floppy disk until we started loading the furniture textures. And then when you actually see it all and it's all there and it's all present and it looks good, we actually start loading high resolution for things like this floor. And then afterwards, while you are already using the tool, we are loading the rest for making furniture look really nice. And for instance, the crinkly leather here and stuff. So that comes last. So we're making sure that the user gets something very, very early on. And they still get a static 3D image of the flat or the office, even if they have nothing enabled, like no JavaScript and stuff. So that's pretty good. But now what else can we do? So first things first, there's things like buffer geometry in 3JS. Actually, the point being, try to load it in a binary format. Do not try to sort of load it as a string and then parse that into floats, because that's really, really slow. So sort of try to load it in binary and actually sort of directly put it into a typed array from an array buffer, and use that to not have more conversions than you actually need. Share materials, so you might have seen that we had one kind of chair like 20, 30 times in the same thing, in the same model. Don't reload this all over again, because it's going to be put into the VRAM every single time. Use references. It's a bit tricky because you have to be really, really careful when you clean up after yourself. Like if you have these 5 chairs and you delete one and you actually delete all the textures, then you get a black blob. Good thing is there's in WebGL 2.0 it's standard, in WebGL 1.0 it is still an extension that might or might not be there. Hardware instancing basically allows you to just say like, I have object X and I want to have it rendered 5,000 times in these different locations. So you basically only have a 5,000 item array that basically says where to put it, but you don't have to sort of do this all magically yourself, but they actually take care of you. Do the reference counting for you, really nice. Combine geometries, so if you don't have to have every single thing be interactive, put it in one large model, because actually the overhead is quite large, because basically what's happening is, on the GPU, if you have 5 models, it goes, model 1, load, take this one, draw, stop. Load, take this one, draw, stop. If you have one large model, it does all the memory transfer once, load this one, work on this one, draw, done. Much faster, especially if you have large amounts of models. It's not always feasible though, right? For us, it's important that you can actually edit single walls. Tough luck. There's a technique called level of detail, which is brilliant. You would have seen it on the GIF for the mountain scan. Basically, the farther away you are, the fewer details people will see. So use very low resolution images. And only as they come closer, as long as you don't give them sort of teleport capabilities to directly jump there, if you know that they have to sort of move there, take this time to, whenever they come closer, load the next image, and load the next one, and load the next one, and unload the others. So yeah, you sort of roll the right level of detail in for each of the users. Cheat. It's the simplest thing. Lighting calculations, I said that already. You have to sort of fire virtual light rays and see how they bounce off things. Very expensive. Don't do that. Use a thing called a light map. So here in this texture, this thing is blue, but on the server side, you can render on a proper 3D engine like Blender, for instance, or 3D Max. You can say, hi, I have this light source over here, I have this object here, and then it sort of automatically changes the brightness of the texture so that you just map this on and you just load an image. No more light ray calculations, no more vector math, no nothing. You just like, image, object, done, and it looks awesome. We do this quite interestingly, so we have a bit of infrastructure in the background. So here you see how this looks when it's loaded straight off the first couple of stages. So it looks pretty crap. You only have textures here, but no lighting, right? And then we send this information to we have sent this information to the server at some point, and within 5 seconds, we've rendered how this light looks, and then we sort of map it together on the client, which only takes like 2 milliseconds on the GPU, really, really fast, really, really easy, and it looks pretty good. Obviously with the drawback that you can't easily just move around the light, because you would have to re-render, but it's 5 seconds. People don't care. We figure out, we're like, oh shit, we have to bring this under a second, because if it takes like more than a second, people will complain. No one ever did. So, no biggie. Cheat more, right? So here, there's an image missing. Bugger. Basically, it's more or less like this texture, but very, very colorful. So you can actually also save calculations for figuring out how the vertex normals go, or the face normals go, because that also takes time, right? You have to figure out like, okay, I have these 3 points, and this is sort of like where they face. Don't do that. Just put it onto as a color-coded as an image color, and I'll just go like, this pixel is green, so that means it faces there. Much easier, much fewer calculations. Bump maps also quite interesting, so if you have to sort of have a high level of detail, but you can't be bothered to actually make high level of detail thingies, this is just a normal sphere, so this sphere plus this texture, dark says it's inset, bright says it's outset, and then you get this. It looks weird when you do shadows on this, but hey, it's kind of good for most of the cases. Now with that out of the way, we get to the bleeding edge stuff, WebVR. So WebVR became interesting because hardware was commoditized. So we are seeing a renaissance of virtual reality with things like the Oculus Rift or the Cardboard. They are slightly different. Now you can obviously argue like, okay, not everyone has a smartphone, so smartphone is like $300. And, like, huh? And actually this DK2, so I'm sort of misleading you here because I couldn't find an image for the customer version that came out or is gonna be shipped soon. This one is actually $599. This one was slightly cheaper with like $399. Oh yeah, so much cheaper. And you need pretty beefy hardware as well. So this is for your hardware, because if you're not having one of the latest graphics cards, tough luck. Oh, you have a MacBook. Sucks to be you. So this is quite cool, especially cardboards like this. So you can actually ship a cardboard for like €2 from China with free shipping, because the European Union screwed up their free trade agreement with China. This one is slightly more expensive, but it's not made from cardboard, it's made from plastic. Very solid China plastic, as you can hear. It costs like €10, so it's not that much more expensive, but it's really nice. You can adjust the eye distance, and you can actually adjust how large your phone is. I have a pretty large phone, so that's kind of handy. But there's obviously drawbacks to the very cheap one, right? The good thing is it works with pretty much every phone. The bad thing is it has no idea where in the space you are. So you actually know where the user is looking at, but you have no idea if I just move around a bit, because sensors just can't do it yet. Also, the quality differs a lot. Like this one is actually not as nice as some of the cardboards. If they are really done really well, the lenses are pretty good. This one is pretty crap, but it's good enough. And actually, it doesn't sort of squish when I actually travel with it. So the quality is not very predictable. On the other hand, the quality is very predictable for Windows computers with really beefy hardware, for the Oculus Rift, and you have got position tracking, so you can actually move around in the space. There's others like Steam VR doing the same thing. It's pretty cool, but the requirements are just incredibly high. The cool thing is, it is available in Firefox and Chrome. In Chrome, you have to download a very safe and securely made build from one Chrome guy from a Google Drive. Just tell your users it's fine to download Chrome from a Google Drive, it's safe. For Firefox, it's in the nightly. Chrome still hides it behind a flag. Firefox needs an add-on for Oculus Rift, though. The spec is really, really early on, but actually quite great already. And there's polyfills available, especially this link takes you to, the slides are online, don't worry. The link takes you to a thing that actually allows you to use keyboard and mouse if there's no headset enabled. So you don't have to write code twice, you write one piece of code, and actually figures out, oh, is this VR enabled or not? So that's quite lovely. The WebVR specs specify two things. The HMD VR device, which is the head-mounted display. That's the thing for your face. And the position sensor VR, so that's doing the rendering bits. The position sensor VR device is also kind of for your face, but also for the camera tracker that the Oculus uses that figures out where in space you are and where you actually look at. Position obviously is not available for cardboards, sorry. And this is how you use it in 3JS. So you have, in 3JS, you have to have a thing that renders, okay? And you have to have a camera that you sort of look through into the thing that you're gonna render. And here you're just like, I want a VR effect on the renderer, which does it cuts it into pieces, it makes sure that the cameras are being sort of doubled and the distances are correct and the distortions are correct. And then you say, I want the camera to be influenced by where I look and where I am. And you say like, here, this one checks if I actually have a VR browser and hardware or not, and then just render through it. If there's no VR hardware, this one uses a keyboard and mouse, and the renderer just renders one piece, so you don't get the weird Oculus-like screen. There's a couple of things that we're gonna have to figure out in the future. I didn't put a picture for motion sickness because a guy vomiting or a lady vomiting would not be so nice on a presentation slide deck, I guess. Motion sickness is a bit of an issue. There's ways to figure that one out. For instance, put in a fake nose, and your brain goes, yeah, it's fine. Okay. Another thing is natural interactions. So this is using a leap motion, and you see your hands, and you can actually do this, and then these menu options come out of your fingertips, which is quite creepy, but quite cool as well. And then you can use your other hand to sort of like manipulate them. It's quite fun. Another thing that's a brilliant GIF, there's devices like the Google Tango. It's not meant for what we are using it for, but Google said it's cool. So because I said we have no position tracking, Lenovo wants to put out a phone with Tango technology this summer or next summer. So basically this one has a 3D laser scanner and figures out where in space you are. So you can actually, so this demo is me, and I can show it to you later, is me in a model walking around in real life and actually walking around in the model, which brings interesting problems because you might be in a really large room and then you might have an apartment in, I don't know, Zurich, where you have a really small apartment, and you might be, oh yeah, that's like, I can walk over these green meadows, and you walk straight out of your window. That would be bad. There's research being done on what's called redirected walking, so that you actually spin yourself whenever you hit a wall, or about to hit a wall, you would spin, and you think you spin around like only like 180 degrees, but you're actually spinning like, I don't know, 90 degrees or something, and sort of make room more usable. So that's coming. That's the next big thing. And with that, I'd like to say, with VR being the next frontier, WebGL shouldn't be the next frontier for you guys. If it makes sense, use it. Don't build this thing from Jurassic Park, please. It's a great fit if you have to talk about space. And it's actually interesting for storytelling because you can put people in the middle of things. And yeah, if you ever find yourself in performance issues, don't fear, don't worry, just cheat. The human perception is quite faulty. So that works pretty great. Also, VR is a big thing, and you can try it out right now with your phone and a Google Cardboard. Definitely recommend trying it. Have a lot of fun with it. Tell me what you built with it. Looking forward. Slides are online already. I'm available on Twitter. My brilliant team is available on Twitter as well. Visit us, and yeah, if you have any questions, and we actually have time, I'm not even sure if we have time still. Awesome. In that case, any questions? Or, well, if you, yeah?
Just the problem, like you said, cheat. I used media 3D classes with using a fake, really old video game.
Mm-hmm.
So they cheated really a lot. You see, most of the games are not even remotely playable because of the cheatings. UI stuck in your face and stuff like this.
Yeah, okay, don't cheat badly. All right, if your teacher sees you cheating, don't blame the cheating. Still a valid strategy. Yes, I see what you're meaning, but yeah, obviously there's sort of things where you have to make sure that it looks good, but a lot of times you can actually sort of fake it until you make it. and we're on the way to actually making it. So graphics hardware becomes more powerful, software becomes better, and you can actually do a lot of things with that. Okay, cool. Yes?
Do you think that something like the gradual stuff you showed with the monk, for example, is this will always still kind of keep being like a including an add-on? Or do you think that 3D is that will become more common in like I don't know, like
Mm.
default use cases where people will actually start using 2D things because hardware is currently 2D?
Depends a bit on what's your default use case. So for instance, YouTube experiments with VR for video, where I think it makes absolute sense, because you kinda, so I have a relative that suffers from a pretty heavy case of social anxiety, so he can't really go out and see places because he's like super freaking out about it. And when you show him pictures or videos, it's kind of okay. It's the best he had so far, right? But it's still, you're not there. Obviously, you're not there with virtual reality either, but it feels like you're there with virtual reality. There is like, you have this framed piece, and you look at it, and you're like, yeah, it's kind of nice, but how did it look like when you actually turned around, and and that's why we do panoramic photos as well, so that you sort of get a glimpse. But if you actually, I put on VR glasses for him, and had a photosphere that covered the entire view of when you stand on Uetliberg in Zurich. And he's like, oh my God, this is amazing. Oh my God. And he actually didn't take it off. I'm like, you should probably take it off because you might get motion sick. No, no, no. Oh my God, this is awesome. Oh my God, I could land down here. Oh, my feet. Actually, that's your feet. But oh, that is great. Awesome. And I'm like, okay, I gotta be waiting over there. Just, I gotta get a bucket just in case. He didn't vomit. That was good. So it's really a different experience. And YouTube experiments with that. And a bunch of other companies experiment with 3D right now. Games, architecture, product visualizations like cars. I think we're gonna see it more and more, but it's not the default use case. If you have a management interface for a router, it's probably not gonna be in 3D. Hopefully not, or we end up in Jurassic Park.
Is that also being used for augmented reality?
Yes, there is people and companies playing around with that. It's a bit tricky to do in JavaScript though, because it's not really good at parallel image calculations, but it's working. I've seen demos of it. I've seen people using different types of markers, for instance, on the web, or you can actually sort of do low-level augmented reality where you just figure out, like, if I stand here and I look in that direction, I should see the church. So if I want to navigate, I could literally look like I actually see the camera picture, but I see like, here is this church in 500 meters, here's that in 500 meters. So that's very easy to do, in fact. So maybe you can use that, and you can definitely combine it with 3D artifacts. So you could theoretically, when you know where someone stands on a field and where he or she is facing, you could, for instance, show a 3D model, like show the camera picture on the phone or tablet, and show a virtual 3D model of a building that's no longer there. Like in Rome, for instance, you could sort of do that, I guess.
Yeah. Translation is also really exciting.
Translation is exciting, yes, that's true. General augmented reality, virtual reality is like, whoa. The 90s called. They give us cool stuff.
All right, I'm the bad guy, closing the list, but
Boo.
it was amazing.
Thank you very much.
So much for being here. Martin is around for today.
Yeah,
the whole day,
well,
so
not the whole day.
when you're leaving? About
Around 2:20-ish.
okay. So if you have questions,
Grab me.
yeah, he's still here. Thank you very much.
Thank you for inviting me. Thanks.